All right, so welcome back to the MG6039, the applied computational modeling. Last week, I asked you to try the activity or the question related to stress concentration. How many of you done it? Good. Let's check answers. That's a good thing. So I have a hidden file here, which I'll make it now show. That is actually the hidden file where is the answer for the PowerPoint and as well the SolidWorks files with the simulation. So I already downloaded the presentation, so I will go through it step by step to explain the process for this stress concentration. So first of all, you will follow the instructions to perform the dimensions. This is a topic we used to cover in Strength of Materials 1. You have the following equations is the stress equals load divided by area. And the maximum stress is you need the K value, which is the correction value times the nominal stress, which is acting on it. Based on the simulation or based on just looking to the problem, we predict the most weakest area is where is the hole, that one. And you can see that in the simulations, but also based on the problem we learn, we need to study as well where is the fillet, where is the narrowing of that section. So usually we use two of these from the chart, figure 2, the K values, one for the hole. And we need to be very careful when we read the dimensions, like the big D is not diameter, the R is the radius of that circle. And then you find the R over D, the D is the distance remaining, whatever is that D minus 2R, let's say that way, and you get that D, the ratio. You intersect with the line, and then you go and read on the left to read the K value and multiply it by what you found, and we compare between the calculations, because this coming from experimental results, and between the FEA analysis. The same thing here. R is the radius of the fillets. The D small letter, it's representing that. And the D capital representing the biggest one, not the hole, the biggest one without the hole. And then we find the relationship, the radius of the fillet divided by D. And you intersect with D over D, the ratio between this distance and this distance. We create you one of the lines, and then you read on the left side the K value and compare between them. So I wrote step by step how you do that. The boss extrude, use mid plane, and the distance for that at 12.7. And then when you try to create the hole, also you cut through the blind cut, and then you generate. The material is ASTM A36 steel. You select that from material properties. And also you will apply fixed support at this end and a load with the value 22,241.108 newtons, that direction on that face. You will find that we could generate default mesh, just default. We don't touch anything. We just click and run and tick the accept green. And then we can do a fine mesh. We don't use the value yet. Today we'll try to use values. We just put the things to the fine side, and then we compare the values. So we came to at the hole. We found these ratios when we put the values. 25.4 divided by 2 millimeters divided by 50.8 will give you the R over D is around 0.25, and you intersect the 0.25 to that line, you will read the value 2.43. That's my guess from the chart. Maybe you're less or more. It's okay. The errors we accept from charts always. And then you write the equation. Stress is equal what? Load divided by area. We need to make sure we get the right area. So load is 22,241.108 newtons. Divided the area. So the area is all that distance, 76.2, minus the diameter for the hole, or 2 times the radius. That will give us the value for it. But we need also to take the thickness for it, because it's an area. That's only we took the longitudinal length. We need to take the width as well, which is the 12.7 millimeters. You will get the values around 34.473 megapascal at the hole. We multiply that stress maximum times 2.43, which we found from the chart, you get the value 83.77 megapascal. My analysis for that one was 83. For the fine mesh is 83.17 megapascal, and for the fine and control mesh, I use 83.751. So control mesh, is very interesting. You just focus on the area where it's high stress. It's saving my time for computations. I don't need to make it all fine. So I'm just showing you. If it's only fine, is 83.17. But if I want to use only control mesh on an area where I'm interested, and usually you do it after you know where is that area, the critical areas. So you don't do it for the entire geometry. So I know like my weakness will be around this point. I compare between the calculated one. So the calculated one is 83.77 and the FEA is 83.751. I'm using the fine mesh and control. I'll get very, very awesome error. You don't get that a lot in FEA. It's 0.024%. And if you don't know how to calculate the error, I left you an equation here. Did I? You can, that equation here, how to calculate errors and direct you how to lead it. Very simple. Okay, now after that, we can right-click on the fine mesh and control mesh to compare between them. We can just find the properties for the mesh, which we learned last week, to get the mesh control details and what is the size for it, because you'll ask me, how did you get that? So I set it up to 0.2 size, the ratio is 1.4, and then 2 edges I selected and 1 face, just for the face for the circle from inside and the edge and the face inside of the circle. So 2 edges, 1 from that side, 1 from the other side, and the internal face for it. Right, now we do the same thing, but for which one? For the fillet, this side, following the chart we have here. So I follow the values, R over D. So radius of the fillet is 12.7 millimeters divided by that distance is 50.8 millimeters. You get 0.25. So I'll go that 0.25. Now D over D, this is 76.2 divided by 50.8 will give me 1.5. So that is the line for 1.5. So I intersect with that line and I read around value less than 1.8. So I will go 1.75. Hopefully you get close to that value. The load is again, but I need to select the right area. So the area will be 50 times the width 12.7. That should be not inch, sorry. That should be taken the inch too. It's millimeters. Okay, and that will give you a value 34.473 megapascal. You multiply by that correction factor 1.75, then it will give you up around 60.329 megapascal. Remember, this is not the weakest area. This is the second weakest area because it's showing like there is a high stress distribution. Now, what I got from that, you will say, what did you get? If I select only von Mises, is only showing me the maximum, which 83.71 is actually here. But if I want to really know that, there is you can use the prop, and then from the prop you select that edge, highlight in blue, and then you can plot it. And when you plot it, you find the maximum value here, which is giving you a value 61.25. So at the distance 0.18 from that fillet or that edge, with the maximum value 61.25 megapascal. And mine is 60, the calculated one, 60.32. The error for the fillet is 1.5. And the reason you say why you did that, because I haven't used control mesh for this one. I could improve it even, and I can use control mesh, another one, only for the fillets, and then see how can I improve it to get a nice value. But 1.5% error is acceptable, is actually more than acceptable. The one where we say it's a good is 3. 4, okay, if it's complicated and is assembly and got many things. 5, I start thinking, can we reduce that? More than 5, many things are wrong. We need to go back and see what are the assumptions we have used so we can work around them. So this is just a typical example. This is very useful for your like question. I know we don't have that chart for the assignment one. Assignment one, you need to duplicate the same thing. You perform the calculations, you have the stresses, if that is deflection or cantilever or cut, and you compare between what you have and what you're getting, and you need to measure that area. Now, because you have the CAD file, the area you don't need to measure it, you can use evaluate. You say, hey, my shape you give me, or any shape you give, when you design it in CAD, you use evaluate, get a section, highlight that section, will give you nicely that area you're interested in. And you use the area, instead of multiplying I did here, you just use the value from the CAD. And then the stress, the load you're applying for it. So if you're weighting scales, you measure that. And that could be for any geometry. So that is the question we just worked on last week. Any questions? Any questions? All right, so that's good. So again, how can you find all this information? When you come to the topic FEA single parts, you find that I put everything, that presentation I just show you, single parts, and then you click under week 3. There is a folder, stress concentration files. You click on that, and then you can find the one which I give you initially for students, which is only the 2 slides, and that one with the answers. And here is the model, everything you can see in it, the SolidWorks file when you download it. So I made that one is visible. Now you can see it and you can go through it. All right, today, save, don't save. Today we start with a new topic. It's called assemblies. Assemblies is the same like previous one, the previous topic, which we presented. However, instead of single parts, we will talk about multiple parts. And we do today multiple parts. And that means the software, SolidWorks, needs to understand what is the nature of contact between these multiple parts. Do you want them to be welded? Do you want them to be free? Do you be bonded, or whatever options you want to choose? There is something when you go and find the information from SolidWorks itself, it can present for you the bonded contact. This is one of the options always offered, the software, which says the program bonds the set 1 and set 2 sources and target in titles defined in the context set property manager. Bonded entitles behave as if they were welded. So when they move, and you can see it in the video here, they will correspond to each other movement. They act like they are two, and they are really going through it. And that's good when you have a bending moment diagram or you want to go through it. Now the other one, think I was going, the non-penetration contact, and showing you the difference between them. I was just searching it in the help. Find it. Just speeding up the video. That is the non-penetration. You can select it to be between surfaces and sometimes even between an edge to edge. And softwares like SolidWorks, they start removing non-penetration. And you see that used to be available in the old versions. Now when we go and see what they have and replacing for it. So here, the definition for it, there is a video for it. I'm trying just to find it here, non-penetration contact. I show you why it looks very interesting and very funny. Maybe. Yeah, so that is the video for non-penetration. When you look at, see what's creating the gaps between them, and kind of like they are not attached, but they are corresponding, because if I'm link to that other part, it will generate for me something to make me like, now they call it free, actually. They changed the name with the new edition. And there is another option, which is allow penetration, which you will go through them, the free contact. That is the free. See what's happening with the free. They give you a wrong messages, kind of like the part entering to inside the other part. And that's like is wrong. Doesn't work with solid metals. Only if there's something they go and melt in each other. But it's something wrong for this type of free contact. This was, I think, the edition 2016. Things they've changed since that time, but I found these videos very good to explain why contact between parts is very important and how can we understand the interference. So when you have pins is the most important thing, because pins, they try to cope with many different forces around them. Shear force, one of the most important forces, impact on a pin, and we go through them. So that's mean there is an extra things in SolidWorks. When we start setting up, we need to develop the contact parts. I developed some materials for us today to show today, and then we can start with a tutorial. So we start with something, and then we go through it step by step. So if you are with me, I will put the week 4 assembly analysis, and then you can download the week 4 assembly file analysis. So that is the CAD model. The CAD model will save you from going through it. I think I downloaded the CAD model. Let's close this one. Don't save. Open. I'm using my downloads, which is not a good idea. I don't recommend. And this is a very good example. It's actually developed by SolidWorks company itself. They use it for different applications, such as the vibration analysis when you have an engine on a brackets. So I'll give you time to download it, and then I'll split my monitor to 2 halves, so I can show you what we'll be doing. And then as well, we go through the PowerPoint slides. Downloads, assembly analysis. So what we'll be doing, this just to explain it, an engine sitting on a bracket. And when you have this bracket, if you can see, there's a lot of parts of it. So it's designed with an assembly with multiple parts. And we would do the simple analysis for first static analysis. And then later I'll show you more advanced, how can we study this and we compare results between them. But something I want to do here, I'll introduce you to something. In the past, previous examples, we used to set fixed boundary conditions. Where is my fixed support? But also we used to fix or apply loads with a value. Now, in this case, I don't want to apply load. I want to apply the weight of the engine. So we learned that something as well. How can I make that engine looks heavy and going through it? Even the engine looks floating, because it's a mechanism, we can make it to be float in the system, and later we can take it into consideration. So first of all, the materials are all specified for me for simplification of this example to be alloy steel SS as a material. And I'll show you how the process to take that engine, I will convert it to mass, to make it as a mass and exclude it from the simulation, because it would take time for finite element analysis such as meshing. And then we set the basic contact for it, and then we compare the results and we can see how can we improve that contact to understand what it looks like assemblies. But first of all, if I tell you, what do you expect? How many contacts are there? You say there are many actually. They could be this bracket or this bracket with this one, identically here. And this one is with this one. and this yellow one with this, and then you go to say this, not really, this one with this as well. So again, many different contexts. But if I'm not confident about that, you can go to evaluate and click on interference detection. And then you say target, consider, or show, or ignore. There are many options here you can see on the side. I'll use the normal one. Calculate. No interactions because I haven't selected the right one. Create person, show, treat concern interface, treat sub. No, I had it in the list here. So target and make in. Yeah. So when I click on treat coincidence as interference, it shows me all the possible interference in my design. And then when I come here and I select these one by one, control, I keep selecting control. It's a long list. Control. Hopefully I hadn't missing anything. It's showing me these are all the possible interference between the multiple parts. So all of these, they have contacts to each other. Part contacting the other part, and you go through it. So that is the best way to identify them. So we always go to, I say, evaluate is helpful to measure areas and stuff like that, but also it's helpful for us to get the interference detection to see how many things in it. Of course, will not help you, but you will know where are they, and you can go through them. If you have any questions, ask. So I'll go again. If I come and click here, evaluate, interference detection, and then make sure to click here and make interference part transparent, do the calculate, and then you can find them. And if I'm busy, like I don't want to go them all of them, you can just click one by one and you can see which one is highlighted for you. And now something you will say to me, how do I know that interface? See, that interface is showing me it's the edge. So technically, you say, do I select that one or that one? I may select this one because that will represent the edge. So that's another things will decide for me. So possibly I'll select this edge or that face to represent the entire system for it, or the edge. Again, you will find those things. And then you go on, like explore. I'll give you time, just explore it, see how many interfaces are happening in this geometry. There are many, right? I'll come around, keep you on the right direction. What happened? Have you downloaded the file? Yes, double click. You must open the file with the other files because the other files are with it, supported. Have you unzipped? You need to unzip the file. Yeah. No, close this one. Close the current one. Close that one. This all works. Close. Okay. Not the entire solver, just the window. So open new solver. You work. So you need to open it from open. Yes. Working for you now? Well, what's going on? Oh, you started in. So you go and unzip and then open. If you unzip it, and or you're opening the other one, will not work for you. Okay, so close. Go file open. Find the location. Where did you put? No. Download. Go which one? It's zipped.
Right. That's okay. I'll save it on the one.
Yeah, see, that's what I'm saying. If it's zip, will not open for you. You need to unzip it and go to the unzipped file. So you need to find where you need to first unzip it. And then when you move it, you need to unzip it. Otherwise, it will not open for you. No, just unzip it, go to downloads. Right click on it, extract all. And now extract. Now open that one, not the other one. Okay, so you need to extract all to open a zip file, or you can just copy paste that folder in it. SolidWorks doesn't work with zipped files. Give you more time. I'll pause the recording, do not make it long. So to set up materials after we investigated the interfaces, we go to new study under simulation, and we click static study, static one. We expand the tree for the parts. I will select them all from parts, apply material. Either I find them or I just select here, alloy steel, SS, apply, close. That ensured for me like these parts, they got the materials. And again, we make it as for simplifications, all of the parts made of alloy steel. And that means we take the density for that engine, we take the Young modulus, we take the yield properties and everything for them. So now I want you to set up the materials. What is happening? Which type of error? So where did you stop? In download. Okay.
Well, it needs to be more scientific than that. Need to just look at the cantilever. Fix one end. Yeah, this one. I already simulated it. So if we fix this end, then apply the load to the hole. So
Okay.
tie something.
So now we need to set up the materials. So I will please set up the materials. Right click on parts and then apply materials. And then you select alloy steel SS. So before that, you need to start the new study. Have you started the new study? You need to hurry up, guys.
Have to be SS, does it?
Yes, alloy steel SS. Right. Can you set up the materials? Yeah, all right, good. Have we started the static study? Yep, so you go to simulation, new study, static. Yep, it's already there. Click OK. Right click on parts, apply materials, and then go down, alloy steel, then click apply. Okay, done it. Right click, apply materials, then go down, alloy steel SS, and then apply. Okay, close. Right, so now we selected the material. What we would do, I don't want the engine to be in my simulation, but I want to take it into consideration. So I don't want to delete it. I want to still using it. So engine is here. This one is the second file. You see when I click on it, it's became blue. Right click on it. You will get an option, treat as remote mass. Treat as remote mass. You click on it, you see will be asking the question, do you want this to happen? And say yes. What around? I want that remote mass to be around these faces where they are kind of like the holders for the engine. So you see those four? I'll leave them highlighted for you. So you select these faces. Are you with me or are you still behind? So right click on it here. Right click on engine. Yeah, right click. Treat as remote mass. And now select what I've selected on screen.
All selectors.
You there? You select those spaces. Remove the selection. Select. So select those. You see in yellow? You select those.
Yeah. All four.
1, 1, 2, 2.
Oh, yeah.
Yeah. So you select those, which is just to get the mass for it. Okay. Check. Done? Done. Okay, you tick the green. It's mean accept. We're happy with this change. And that's mean what will happen, the engine will be kind of, it's taken out from the calculations, but is there. We treat it as remote mass. And you can see it became not like it used to be. And you can see as well, the transparency of the engine is kind of suppressed, but it's became under here. If you expand remote mass, you see it is already there with alloy steel and everything in it. All right, let's do the next step is applying connections. The new things, what we do in this session, in the past, we used to not have connections. We used to have what? We used to have nothing, just one part, and we escape connections to go to fixtures. Now we need to stop at connections. So with connections, it's telling us we need to do the following local interaction. The type of these connections are bonded. The type of connections I want to do, first one, is this with this. I would do it one step with that base. And that should be applied as well with the other side. For this and this with that base and that base. So let's do it step by step. I put an image here to show you step by step. So I enlarge that one. You can always enlarge it. And the type we say is bonded, and we go through it. So it's actually, this one is better because it shows you everything, how it is, the pink and the red. So right click on connections. I will say insert local interaction. Right click on connections and click on local interaction. Local interaction will ask you what do you want to type for this. Manually we're using. The type, we made it bonded. So there's a free shrink fit, virtual wall, and contact. So I'll choose bonded. And I'll choose here the 4 things which I mentioned here. So which one? Look carefully. 1, 2, 3, 4. What are these communicating? I'll leave you, just give you time to see them, because when at least you can see them. The blue ones will be the top ones. Those edges, the internal spaces, not edges, the internal one. And the pink one, what will be very easy and simple, this and this. So those are the pinks, and you can see them how they are linked to each other or how they interface with that type of bonded. You happy with that? We click OK. If you have any questions, just call me. I left it there, so for you to see on the monitor. But if you have any questions, if you're done, just click OK. Done it? Okay. All right. So just let's check Bonnie and have you done it? The pink ones? Yeah, the 2 of them should be 2. Yeah, this one. All right. So good. So when we're done with this, we accept it. So we have created the first bonded contact between these 2 layers. Which one now next? You see, we're going from down to up. I can tell you the next one is the one you can see it also type contact. I'm just showing you here, like you can see it all in clear. Now we know the blue and the pink. We're doing, it's a bit tricky, the second one, but we would do it. So it's technically this one and this one and the other one from the other side connecting to what? To that face. So I'll do it in step by step. So right click on connections, local interactions, the same thing. And I come to select the blues, the blue color. So I'll select the first one, this and this. And then like the steel base is news trust, and then this and this. So those are the two blue colors. I'll give you time to see them. You can follow me. Yes. Sides. You need to be more understanding your mouse. When you're good with your mouse with SolidWorks, you see yourself faster. Good. Okay. Now, if you're in a head, the pink color, which will represent when I turn it over. So when I come here to select the contact, I'll come and say which one I'm selecting. So it will be that and that one. So kind of like what intersecting between them. And you can see clearly from here. So the blues connecting to that piece. I don't want to select extra because will give me a wrong selection. So you can see them now. The pink is representing that. Again, because I didn't change the type, it should be bonded. So make sure the type is bonded. So another options, you can select the pink. You can see it. It's not that one. So you selected the wrong one. See, it's giving you error. You select. So please don't select for that second bonded. You don't select these. These already we've been selecting them. Be careful. We're selecting that part. If you select the under, it's for the other thing. So you need to select that part. Okay, so it must be the part connect to each other. Like if you select something under, they will be giving you an error saying why you connecting something is not interfering to each other. All right, so happy with that. I'll click OK. Now that is the second one. Now we do the other one. Right click, local interaction again. What do we have left? So we have this one and this one. And the pink one, which one will be the big? Which is the motor base. So the blues with the face of the motor base. So plate 1 and plate 2 with the motor base. You can see them when they highlight each other and very clearly connections between them. So anything, 3 things, they were attached to each other. And they were giving me that interesting result. If you have any questions, I can come. Third one. So you select that face, yes, that face, yeah. And then here, you turn it back, turn it on, down. Yeah. So it kind of like whatever attached to each other.
Is this bonded or contact?
Bonded, all of them bonded, we're choosing here. So the type of contact is bonded, the first one. So bonded, and then you get that face between them. So what I did, every face attaching to other face from part to another part, I made between them a relationship. So we are calling them bonded. And bonded is the one which we tell you, first one, like similar to welding. So they will correspond to each other and they will transfer the analysis. All good. Now, since I'm happy with that, I click OK. So now it's showing you in the my tree here, I have the following connections. Okay. Done? Okay. Now we fix. How can we fix? Fixture. So now we're going step by step. I will zoom out just to go through the zoom. What we'll be fixing this face. And from the other side, this face as well. And we do it for the other direction. So 4 faces we fix. So right click on fixture, fix geometry. I'll select them one by one. So that is the first face. And we come here. That is the second face. It's a bit heavy, right? You feel like the software starts getting heavy. Yeah, because again, when you have big designs, you need a good computer. And then that face, make sure to select the face till you be patient with it if it's slowing down with you, till you see the selection of the face. Select it, don't select edge. I need to see here in my list, face 1, face 2. Now, because I've done a mistake, you see, I see that selected edge for me, so I will delete. If anything's like doesn't make sense to me, I will go and clean it. So again, come back and select this face. Okay, so that is a face. And then I come here, must be the face, not the edge. And then I come here, or bring the mouse, face 3. So those faces, I need to select them one by one. I'll leave it here till I check with you guys. And again, when I need, every time check your selection, make sure if I selected edge by mistake, delete it and bring the face. Perfect, perfect. There. Check face, you have an edge selected, so you delete that edge. And you have vertex as well, must be faces. I must see here faces to ensure I have selected correct. If I see edge or vertex, it means delete and reselect the face. Because the software starts feeling heavy now, you can see it. Yeah, face 1, and then go and select the other faces. This one, face 2. Yeah, if you've done the faces and then accept, click OK. Give it time because now you can see, because we're doing a complicated problem, not like it used to be one part, things start slowing down and more processes. All right. Happy with that? I click OK. Okay, now after fixture, we go to the load. The load is interesting here. I want to take the load of the engine. So right click. Instead of force, I'll use gravity. And will ask me which plane you want to apply this. I'll keep it on top plane. So it needs to be read top plane. I need to see that arrow, the red one, do you see it? Going downwards, the direction of the gravity acceleration. It will read minus 9.81 later. You'll see it later because my y is up and my gravity is down. So it's negative 9.81. Don't worry now. It will read. The most important for me is the direction. If I unclick the reverse direction, will go up, and that's wrong. So I will leave it like this and then click OK. And that is mean I take into consideration the mass of the engine. And then you say to me, how the software understand the mass of the engine? The mass has what needs the density. Density for that materials, alloy steel, SSS is written. Therefore, the software will understand how to convert the weight to a load, which is the same. Mass times gravity acceleration equals the weight. Happy with that? Now we go to the mesh. So we did that, the mass. Now the mesh. The mesh, I will enlarge that to show you what we'll be doing. We'll be a bit pushing it today to the limit. We're trying to do something very cool. Create a mesh, right click on mesh, create a mesh. Now I don't want to do mesh fine and remove that arrow right and left. No, I'll click mesh parameters and put that value to 10 millimeters. So mesh parameters, you click the box. And then when you come here, you see that everything is under the high quality. Define mesh. Of course, you have a curvature-based mesh or standard mesh. I'll use blended curvature-based mesh because my geometry consists of many curves and things. So I'm okay with that. So I'm happy. I'll click OK. Now, when you click OK, if your computer is good, will things will finish quickly. If your computer is the real test of your computer, technically. And that's taking from the RAM, the CPU, and the graphic card to divide this problem to multiple parts. And this, again, for you is a rest to reflect of what you have done. So don't annoy the computer in anything. Let's run by itself, because the software can crash at any second. And we're almost done. It's just after that, it's just run results. Results will take longer than the mesh as well. And that's the process of FEA CFD analysis. It's getting, if your computer is fast, should be finished faster than mine. And okay, it's done. Now it's processing. Don't annoy it till you see the mesh. Perfect. The mesh is done. And we got the things, and we can see the engine has disappeared, but I know where is the gravity center. That's based on center of gravity, mass center of gravity for the engine. Now we're happy with that. I will go to run results. Another time to wait and patiently. So you click run this study. And be patient, don't double click multiple times. The software knows what it's doing and will just let it go smoothly. And my advice for you, if you're using your computer, use other winter computer to do some other work, because complicated designs would take, this one would take less than 10 minutes, but others, they can take 30 minutes and plus. Yes. Yeah, I know. If you have those computer gaming laptops or computers, definitely things will be faster. So you can click on more, and you can see what is exactly the software is doing, and will perform the calculations. I ran it this yesterday with the 64 gigabyte RAM. It took me 5 minutes. This is 8 gigabyte RAM, so let's see how long it will take, and we can anticipate. But technically, that is what is designed when you have not just one part, multiple parts, and an engine, and you want to calculate everything on it and find the relationship between them. Again, if your computer is good, may run it before me. Maybe we can finish it. And I found something very interesting. Some computers at Wintec faster than even the Tutec computer. So if you see it here, sometimes it's faster than you see there. I don't know why. Something within the system. Done yours. Very good.
How do I stop this? You know how to stop this coming?
You can just minimize it, or
No, it doesn't. Makes it bigger.
okay.
I can drag it out of the way.
It
But it
doesn't
just
show up
keeps-
on me.
Keeps
Yeah.
turning up every now and then.
Yeah, possibly. Yeah, it's 9%. And it doesn't show any percentage. No, that's the current task estimate. Now it started 9.1.
What it zooms those those down.
Yeah, I Zoom, yeah, because I'm using other things, Zoom and other stuff.
Mine is stacked with 18.2.
Yeah, I think you missed something with your or something. Possibly when you did the contract.
Yeah, I think this one's got 32. My work 64. Yeah, SolidWorks on top of that one too. Do I get 4 weeks? Is this fun?
Oh, that.
This is one of the things with the CFD analysis, like you can take time and. Yes, we can talk about something else. So, yeah, that is usually what will happen. It will finish at some stage, but I know because if you're using 8 GB RAM, so have you fixed the things? So which one was wrong? Have you used the force? Possibly you didn't have a force. I think I know what you've done. Have you done it? That one is okay. No, it should stop there. Choose this. That's also same. Question mark. No. So that also one, which is that with that was a surface. So that's supposed to be this one. Is this. Yeah. This. This. No, 18%. It's moving.
Yeah, awesome.
It's going here. Oh, it's still something. Done. For me, it's finished. Connection. You selected the edge by saying no edges. Select the face. Face is in the face. This one. They obviously done many selections wrong, and that's why it's driving the software. So you need to go and check one by one. Exactly. But let me here select it. Possibly something else, like every time. All right, so when we get the results, you can explore them. What I always recommend for you is to double click on the von Mises stress and always go to definition, change that to megapascal, and then true scale to see it in the true scale, and chart options, make it floating, and 3 significant figures should be fine. So you can see that chart in a good, with good demonstration values. So it's about the maximum stress here is 9.465 megapascal, and it's showing you where is the stress applied. Now, if I want to demonstrate this with more distributions, I could change that, double click, and it's good. There is no high stress on it because this machine is designed for a railway. So technically it should move right and left. So we can do later on it next week, some vibration analysis, the harmonic, to see how this will correspond to the engine. If I go to the displacement, you see the displacement will give me more information. And again, double click on displacement. Again, when you see these bands, they are exaggerated. They are not true. Just be careful with them. Don't believe them. They are exaggerated. So just go and change that to true scale, and chart definition, make it floating, and then tick OK. You can see the displacement 0.03 millimeters. And make sure to select the true scale. Now, something I show you in the other presentation, if I want to sketch something, I go to plot tools, prop, and I want to see what is exactly why this area is too displaced. There's kind of like high stress here. And then I select on selected entities. You can select this edge or face. I prefer the edge, clear selection. Edge, and then from that edge, update. And if I want to sketch that, will show me interestingly, the deflection or for that edge, which is giving me the value. When I bring the mouse at the maximum, it's 0.03. So that is where it's happening, the maximum deflection or displacement for that section. And if you want to download the data, you can copy, save, or download it as an CSV file or text file. And CSVs you can open by Microsoft Office as a Excel file, and then you can see more interesting information. This is not something we want. Go to my downloads, and I can check that CSV file. And you can see the values XYZ and the components of it and everything. Where is the maximum happening? And there is 0 to see anything you're interested in. Okay, anything else? All good? Awesome. Roddy, is all good there with you? Have you managed to get that simulation?
Yep, that's all good.
Yeah, no drama. The computer run its okay.
Yep.
That's awesome. Perfect. So now we continue with other things, because this is what we did as a good example. But next session we'll do more different types, because you say, what do you mean? Because I didn't tell the software what is the correlationship between this. So I need to go and use different type of connections, such as pin or bolt or bearings. And you can see there is also spring if you have a vibration analysis, like if you want to do spring in it. So next week we will come again. We have assemblies. We will try to perform something to add connectors type pin, we'll go through them step by step. But I think today is enough for the software. The pin would take longer time. So how many pins should be? 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, about 12. 12 because they are from the bottom. Another, this one connecting to this part, and then this part to this part, and go. Yes, about 12 pins we need to introduce here. And then the software will understand there is a pin here. Now, pin, I can do one just very quick demo. Right click on connections, and you click pin, and then we'll ask you, what do you want to pin? Or choose, like, for example, it goes back to the normal. I would say I want to pin this with this, and then as soon as I click OK, you can see how nicely it's pinned with a blue color. And that means the software understands there is a pin, because in drawings, you don't need to draw it because it's automatically understand the software. And I can do the rest of them the same principle. But you see, there is another pin I need to add from that side. So I go again, connectors, right click, pin, and then I select very carefully here this one, and then this one, and then say pin it. And now you see nicely how it's pinned from top and down. Don't worry about it. We'll do it next week. We'll continue with pins and nice things, because I think we exhausted the computer today. It's a lot of things. And then we compare. If I add pins compared to this, what would be my result? So save always this result for you. It's a good exercise, and then we can build on it further information. All right, so now you say what we'll do today. I have very good exercises on Moodle. Non-linear example upload here. Non-linear example. I want you to try the non-linear example. Which one is the non-linear example? Very interesting exercise. You go to help, SolidWorks simulation tutorials, and then you go to simulation standards, not that one, simulation professional. It's one of my favorite ones. It actually should be under the advanced. Yes, that one. So you go to SolidWorks Simulation Premium, and you find that one, nonlinear contact analysis of the pipe. This is a very interesting, just 2 parts, not complicated, and you have the geometry already there. You click here, and then you need to set up everything following the instructions given to you. So that will be the exercise I want you to do now. I'll help you to navigate it if you can't find it, and I'll pause the recording, and because will be just time for it. For me, when I found it, like it's working that way. Yeah, sometimes with the Zoom, it's a bit tough. It's adding extra load on the simulation, but it's fine. We're not doing very complicated stuff.
Like the materials. Work.
Yeah, it's possibly some glitch. Yeah. Now, something else you can do as well, I'm showing you, you can always play the animation, but if you want to see it step by step, you can come here at the end of this von Mises, and you can just click the arrow step by step, and you can move it from step 1 to step 2. So step 3, step 4, you can see those arrows. If you want to take a photo, for example, for each one of those steps, so I was like, okay, I want to see what happened exactly at step 7. I can see really both materials is showing me that non-linearity of the elasticity, because that's something to tell you if it was solid, will break and will not really give you that flexibility. And then if I go and see what's happened after 8 and 9 and how can go through it step by step. So it's very good to choose that at the resulting later when it's finished, and you can show them and explain them in these things. So again, this is another example when you have 2 parts, but the materials are non-linear, and they take a lot of time for setting up and simulation. Even they're just 2 parts, very simple parts. We're not talking about the previous example we did, which multiple parts, multiple interface and stuff like that. This is very good if you want to do a bottle analysis as well. So we have Brody, are you there? Have you done it?
It's not working for me.
Oh, it's something with the materials.
Possibly, I'm not sure.
Okay, let's check things because I was finding like few things could impact it. So first of all, the materials, just sometimes what we experience here, you double click on it and reselect it again and will be activated for you. Just sometimes a glitch in the software. Other thing, material should be fine. The local interactions, you can select them. This, if you made the right selection. So in the blue, you have the faces, that face and that face. And in the pink, you have the following inside 1, 2, 3, 4, 5, 6, 7, 8, and 9 and 10. So those the entire faces. We need to be worried about them. Or 3 to 10. So it's 8. And we'll remesh now for me and take time. What we have as well, that's the normal one, which is just the bonded, which comes by the software. And the fixture, we need to be careful with them. Editing fixtures. So the fixture, you choose use reference geometry. And that reference geometry for the first one is here. And front plane, diameter or dimensions given. Linear view, you need to follow that, the linearity of it, just to check it. And then you come to the second fixture, which we're required to set this edge and the outer edge here, 2 edges, use reference geometry, front plane, and you select as well linear, but would be just set up everything to be free. And then after that, you have the last fixture, which is this one, that face. So have you fixed that face? That's very important. It was not described very well in the question. So that is the face we need to fix. And meshing, just the normal meshing. When you go to create mesh, remeshing would delete the all mesh, cancel, like it's just to go through mesh, and then you run the result. So it's not really, it doesn't have much of complication. But again, when you run the result, this will take now faster because I just did few things compared to the last one. But if my computer is busy because I'm using Zoom or whatever, it will take another 10 to 15 minutes of timing for it. So yeah, it's a process. What I would suggest, like you can do it step by step, and then we go through it. This would take ever for me. So please, if you're done and you got the results, you go to the Moodle session, and then you can find under assemblies. I want you to upload this under nonlinear examples. I can see someone already did there. Just write your reflection and show some images. And if you're done, just call me so I can tell you which one you do the next, which is the crank assembly analysis. Yes. Selected something I want to give it on. Possibly with your fixtures. Reference. Use reference geometry and fixture. Why they ever do that? So if you're done with this and everything is perfect, start with the crank assembly analysis. Otherwise, if you're not, stay with the current tutorial. Crank assembly, you can download it from here. Yeah, so places, this example. Go back. Right.
Thanks so much for picking up that stuff too, Steve.
Yes. Pause my video.